Alrighty, so we need to make sure we have our thinking caps on and our understanding caps on, because we're going to talk about some stuff that we already know and understand, but then we're going to shift that as well. And it's very important that you understand what they have in common and how they are different so that you can keep them separate in your mind as well. All right, so we are talking about sine and cosine today. So it says, so far in Unit 3, we've learned how to define sine and cosine values for angles in standard position on your unit circle, how to measure angles in radians, and how to use the unit circle to evaluate sine and cosine. So those are the kinds of things we've talked about. So now we're going to put it all together and see how we can represent sine and cosine functions graphically. Now, technically, we've already done it graphically because our unit circle is on an x and y axis, but a different kind of graphically. So let's talk about what we've been doing with this here. So we know on the unit circle that these ordered pairs that we have on the circle represent cosine theta, sine theta. We all agree with that? Now, this is very different than other graphs that you have done, because we are used to having something like x comma f of x, which means our x is our input and our f of x is our output. That is not what happens here. Cosine is not my input and sine being my output. My input is the angle measure and my output is cosine and my output is sine. So this is really called the function part of this unit circle is like parametric functions that I don't expect you to know those words. That's not anything we're going to get into. Just know that with parametric functions, your input is not your x or your y. It's another variable, and that's a whole different animal that you can get into in later maths that we're not going to talk very much more about. I just want you to understand that it's different, right? This is not an input-output situation. We are going to transform this into an input-output situation like we understand. But when we do that, we're going to have an input of theta and an output of sine, and an input of theta and an output of cosine. So they're two completely separate things. We're splitting up this circle. So that, again, what we'll end up with here is theta, comma, sine of theta. The next very important thing that you need to remember so that you don't get them mixed up together is that when we talk about quadrants, when I ask you about quadrants or when you're thinking about quadrants, you are still dealing with the unit circle. These are the quadrants we care about. Just think about it. In all of the math classes that you've had, like you talk about the quadrants sometimes, but you probably didn't talk about them near as much as we have in this course because we're talking about the unit circle. Do you need to know how the quadrants exist on? You have a chart test? They weren't open, then you have to go to the attendance office or somewhere else. Here, all I see on this graph is the first quadrant and the fourth quadrant, but I don't care about that being the first and the fourth, okay? When we're doing this type of situation, do we need to know the quadrants? Absolutely. Do we ever really talk about them? No, not really. So anytime we're going to talk about the quadrants, it's because we need to know where our angles are. So like I care about this being a second quadrant, this being the second quadrant because this is my second quadrant, pi sixth angle, that type of thing. So even though we might be looking at this picture over here in this type of function, if we're talking about the quadrants, we're still thinking about the unit circle. Because if you look at your inputs here, your inputs are your angle measures, your x values basically. It's really theta and not x, but those are your inputs. So as we look here, when I go from 0 to pi halves, well, 0 to pi halves, that's the first quadrant over there. So these are my first quadrant angles. Then when I go from pi halves to pi halves to pi, these right here are my second quadrant angles. You see how that works? And then from here to here, those are my third quadrant angles, fourth quadrant angles. Has nothing to do with the quadrants that are over here. We're good with that? Because that's one part of where people kind of get confused. We have to kind of think about them both, but again, they are two completely separate graphs. All right? So let's go ahead and fill in this chart and see what happens with this graph here. So these are values that we should know. Sine of pi 6. What's the sine of pi 6? 1/2. Sine of pi thirds is square root of 3 over 2. What's the sine of pi halves? 1. Okay? So pi 6, pi thirds, pi halves, that took us through the first quadrant, right? We skipped over pi fourths. I'll tell you why in a minute, but skipped over pi fourths. So now I'm going to move into my second quadrant angles. In the second quadrant, is sine positive or negative? Positive. So when I get to 2 pi thirds, it's also square root of 3 over 2. 5 pi 6 is 1/2. And what is the sine of pi? 0. Okay? That got me through the second quadrant, right? When I get into the third quadrant, is sine positive or negative in the third quadrant? Negative. So for 7 pi 6, it's negative 1/2. And then negative square root of 3 over 2. And then negative 1. Then when we get to the fourth quadrant, is sine positive or negative? Negative. So I got negative square root of 3 over 2 and negative 1/2. And there's no such thing as negative 0. So it's just 0. Everybody with me so far? So now we're going to take those values and we're going to plot them on this graph down here, with my input being theta and my output being the sine value. So it's theta comma sine of theta. So at pi 6, my value is 1/2. At pi thirds, it's the square root of 3 over 2, which is about 0.866. So that's kind of what we need to know to be able to just kind of put it right there. And then pi halves, we're at 1. So I left off pi fourths because it's just another weird fraction that we don't necessarily need to get what we're getting out of this. So then when I get to 2 pi thirds, I'm back down to 0.866. 5 pi 6, I'm at 1/2. Pi, I'm at 0. Okay, thank you. 7 pi 6, I'm now, so this got me through quadrants 1 and 2 on the unit circle, right? All my sine values are positive. Now I'm getting into the third quadrant angles. This is where my sine values start being negative. Negative 1/2, negative 0.866, negative 1. Sorry, I was doing better at actually hitting this. Whatever, pretend like that's at negative 1. And then negative 0.866 again. I think I can't do it from this side. I got to do it from over here. I don't know. OMG. Okay, here we go. Whatever. I'm trying to get it right, but y'all are just going to have to deal with it. And then at 2 pi, I'm at 0. Okay. Now you see that sine curve there? Not only that, but there's one we left off, sine of 0, and even if you're not real sure, if you look at this graph that we have now, sine of 0 clearly has to be 0, right? So here is your sine curve. We could connect the dots, but we're not going to because it probably looks better with just the dots there. But there's your sine curve. And then once we get to 2 pi, then we start over again, right? We start over. This is what makes it a periodic function, okay? Also, when we talked about periodic functions in the periods the other day, we're here. One rotation all the way around the unit circle is 2 pi. So one cycle of the sine function here is also 2 pi, which makes that period 2 pi before we repeat. Okay. Now I'm going to show you this. I'll tell you why it's called fettuccine here in a minute. But okay. So I have this unit circle. Now if I move to here, I'm at, so this, even though it's not marked, that's at pi 6. So this angle is at pi 6. I have this blue segment right here, which is my x value, and then this yellow segment right here, which is my y value. The vertical displacement is my sine value. So at pi 6, my sine is 1/2, or where it says 0.5. So I've got this pi 6 and I got this 0.5, right? And so I'm going to, maybe this will work for me. I'm not sure. We'll see if that happens. Then I'm going to move on to pi thirds. It's about pi thirds there. And then, so that's pi thirds. My vertical displacement is greater, right? I don't know why it doesn't like it the first time I do it. Then I'm going to go to pi halves, okay? And I'm going to insert, this says insert fettuccine. I'll tell you why it's fettuccine in just a minute. But do you see how those vertical displacements, those three are different, and my sine values are getting bigger until I get right here? This is the radius of the circle. The biggest sine value I can possibly have is 1. So then after that, they're going to start reducing again, right? But still, all my sine values in first and second quadrant are positive. So if I come back over here and I start drawing, here I get to 1, and then I start going back down to get to 0. Then my sine values become negative, and they're negative in the third and fourth quadrant. And then when I get around to here, it just all repeats again. Okay, it just oscillates like that. Okay, and even if I went the other way, even if I was going this way, I would still keep going to the left. And it could just go on for infinity in both directions. Okay, because I can just keep going around the circle, basically what's happening. So this is called fettuccine because I created this during COVID because we used to do this activity. We don't have time for cutesy stuff anymore. Plus, this took us like 2 days, and I felt like some kids still had no idea what they were doing it. And last year, after not doing it, y'all had a better understanding of what was going on. But we literally, as I was inserting those vertical ones, we literally snapped off pieces of fettuccine that were the vertical displacement on a unit circle that I gave them. And then put the little thing on there. So this is 2 cycles of sine, and we could keep going in either direction. Okay, but this is how we created it. And some people understood that these were actually my links and my sine values, but some people didn't get that. I think we got it better from talking about it this way. But are we good with sine so far? You understand where all that came from? All right, so let's talk about some properties here. Vocabulary we need. Properties of f of theta equals sine of theta. So midline, that word came up the other day. I told you it's literally in the middle, and that's kind of what you needed to know. Midline is halfway between the maximum and minimum values. So here's my maximum at 1. My minimum is at -1. For the parent function, it is just the line y equals 0. It helps us kind of like an asymptote does. So we draw it in even though it's not really part of the graph, like the asymptote's not really something that you see there, but you put it there and it helps you make everything make sense. Then we have the amplitude. The amplitude is the distance. Distance meaning it's always positive, not displacement. Distance from the midline to the maximum or minimum. So I can do this piece here, that distance, or this distance, either one, because it's going to be the distance and it's positive. That's my amplitude. So for the parent function, it's 1. Okay. Then the period. So how long, what are my x values that it takes me to get through one cycle? If I start here and go all the way to here, that's from 0 to 2 pi, then I start repeating. So that's the period there. Period and frequency are related to each other. It's just a different way of talking about kind of the same thing. So the frequency is just the reciprocal of the period. So this says it takes 2 pi to get 1 cycle. This says I have 1 cycle in 2 pi units. So again, but you can use both of them differently. Frequency will come up a lot more in, physics, that kind of thing. And then the graph of sine of theta oscillates between concave up and concave down. So oscillate is this motion that the graph makes. And see, we're going from here to here, we're concave down, then we're concave up. Okay. Now, before you flip it over or anything else, excuse me, somebody earlier today said, is the cosine graph just a reflection of the sine graph in the x-axis? And I said, well, actually, no, it's not. But that's a very good observation to make, because I think what he was thinking was, we know we're using the same values over and over again. It's not going to be the exact same graph, but they have to be related somehow, right? So let's look at cosine. Flip this over. Let's do the same type of thing with cosine here. Once again, this is cosine theta, sine theta. And we're going to turn this into theta, comma, cosine theta. Kind of unrolling the graph. So these angle measures that go around the circle, picture unrolling the circle. That was another thing that was good about that activity. We literally took a piece of string and measured a circle and then laid it out straight to get our x-axis. So we're just taking this from 0 to 2 pi and laying it out horizontal like this. We're just unrolling it. All right, so cosine. Cosine of pi 6, what is that? square root of 3 over 2. Pi thirds, 1/2. What's the cosine of pi halves? 0. Okay, so that gets me through the first quadrant. Starting in the second quadrant, is cosine positive or negative? Negative, right? Oops, cosine is negative. So that means this is going to be a negative 1/2, negative square root of 3 over 2. And what is the cosine of pi? Negative 1. All right, 7 pi 6. I'm now in the third quadrant. In the third quadrant, is cosine positive or negative? It's negative, right? So it's negative square root of 3 over 2, negative 1/2. No such thing as negative 0, so it's just 0. Now I'm on to the fourth quadrant. Is cosine positive or negative? Positive. So this is going to be a positive 1/2, positive square root of 3 over 2, and a positive 1. Okay, everybody good with those? All right, so let's graph that. At pi 6, I am at square root of 3 over 2, so that's about 0.866, so I'm about right there. Pi thirds, I'm at 1/2. Pi halves, I'm at 0. That gets me through the first quadrant. Second quadrant, 2 pi thirds, I'm at negative 1/2, negative 0.866, negative 1. 7 pi 6, I'm now in the third quadrant, I'm still negative. And then fourth quadrant is positive. And the one that we missed over here was 0. Cosine of 0 is 1. Okay. Now, clearly you can see this is not a reflection in the x-axis. But again, that was a very good observation, or to think. It wasn't really an observation because he wasn't looking. He was just thinking about how they could be related. But how could I take sine and make it into cosine? What could I do to the sine graph? What do you think? You can flip it back over and look. Any ideas? Look at how they're related to each other. What kind of transformation could I do to sine to get me to cosine? Could do what? I could, okay, so if I do a stretch, is this bigger than 2 pi though? Now this is a good idea because I've heard that before. You get where you're getting there. If I can't do a stretch and I'm not doing a reflection, what else could I do? Translation, could I just move it over? Like look at my fettuccine again here. So on this graph here, I'll just show you half of it so I can hold it right. So right now for sine, this is my y-axis right here, okay? If I shift it to the left pi halves and I make this my y-axis, does that look like cosine now? Or at least most of it, but that's all that happened, is that we can just shift it over and then it's the exact same thing. All right, you see how that works? And because of that, these are both called sinusoidal functions. Cosine and sine are both sinusoidal functions. That's your sound waves, any kind of frequency waves that look like that. They are all sinusoidal functions. We will write functions that are sine and cosine, but technically, I could do everything in sine. I could get away with never writing a cosine function because I can write them all in terms of sine by just shifting it over. I mean, cosine exists for lots of reasons, but that's what's happening here. So let's talk about these properties down here then. And then we'll talk about that a little bit more. So this is for cosine theta. These are really, the properties really are the same. Midline is still halfway, so it's right here. Amplitude is the distance from the midline to the maximum or the midline to the minimum, but it's a distance, so it's always positive. Period for cosine also is 2 pi. We just think about it starting in a different place. And the frequency is the reciprocal there. When we're talking about period, just like we did before we started talking about trig functions, I could start anywhere to count it. So I could start here or I could start here. I would need more of this drawn to be able to figure it out, but I could go from here to here. But if we can start at 0, that always makes it a little bit better because then we don't have to do the adding and the subtracting of the pi stuff very much. When we know we're talking about cosine or know we're talking about sine, you're going to need to draw a little parent, sketch a little parent function. And it's way more important and helpful than it is on any of the other parent functions I've made you do that on. So for cosine, we know it starts up here, and we just need to draw one cycle like that. And some people even, kind of either do, okay, so if you get the zeros and stuff mixed up on your unit circle values, if you know that this is what cosine looks like, then cosine of 0 is clearly 1, not 0. Like this visual can help you as well. So both functions, whether it is the unit circle itself or this, can help you with what your values are. And then go back to sine, because we didn't do it on sine, but we need to do the same thing. In sine, the little parent function would look like this, okay? And then there's 5 key points. There are the beginning of the period, the end of the period. For the parent function, here, this is 0, this is at 2 pi, but I can change the period, but no matter what, here's the beginning, here's the end, here's the middle. And then halfway between these 2 points will be a maximum, and halfway between these 2 points will be a minimum, or vice versa if they got reflected, but everything's half, half, half. So not only we're going to have that, but we're actually going to mark on our little parent function when we do it to help us figure stuff out, right? Everybody good so far? All right, so let's go back over here then. So this is what I just said about the sinusoidal functions. The sinusoidal function is any function that involves additive and multiplicative transformations of f of theta equals sine of theta. So sine and cosine are both sinusoidal functions because cosine is just sine shifted to the left. And when we get to our transformations, you'll see that they work just like they do in every other function. Some of them have some different names because it's trig stuff, but they still do the same stuff. Okay, what questions do you have right now? All right, so I'm going to give you page 2. The back of page 2 should look very familiar because it has this clock on it that we did on another one. We're going to answer some different questions about the clock there. I think that's 5. I'll come back if it's not. Oh, and I just realized I forgot to do what I forgot to do in third period as well. All right, before we move on though, let's look at cosine this way too. Okay. So when I rotate here to pi sixths, see my blue line is my x value, my gold line is my y value. So that blue line is my horizontal displacement. My horizontal displacement starts here at 1 because it's the radius. Then that horizontal displacement gets less and less because I'm getting here 2 pi halves where my vertical or my horizontal displacement is 0. We know in quadrant 2 of the unit circle, cosine is negative. So my cosine function, the values are negative here. In the third quadrant, they're also negative. And then when we get to the fourth quadrant, your cosine values become positive again, and then it just starts all over. Okay? You see how that works? Also, because somebody did this for their neighbor third period, and I got an oh, and I was like, oh, I should have done that for everybody. So look at this right here. I don't know how far to the left I can draw, that this will let me draw, but I think somebody was having a hard time seeing the shift. So since you can continue and go on and on, if I make this right here pi halves, or negative pi halves rather, then this is where like I would start here and go to here to get sine. I just shifted it over and it's what it made cosine. Okay, so do you see that? You just shift it over and it looks the same? All right, I'll take that as a yes. Okay, next page then. We're going to start here. We'll look at the clock in a minute. Going on page 89. So they have given us a graph, and it tells me that 2 periods of the sinusoidal function f of theta, just because it says sinusoidal doesn't mean you have to think about it as sine. We could think about it as sine or cosine. We're going to find the period, frequency, midline, and amplitude. The easiest thing, I believe, to do first, and probably the most helpful, is to find the midline. if my maximum point is at 6 and my minimum is at 0, then halfway between 0 and 6 is 3, right? So here is my midline. And the key word, or the key point in midline is line, so I can't just put 3. My answer is y equals 3, because it is a horizontal line, just like you would for an asymptote. Okay, everybody good so far? Then, probably the next thing that sometimes comes up when you're looking for the midline is the amplitude. It's the distance from the maximum to the midline or the minimum to the midline. What's that length? 3. Between 3 and 6 or 3 and 0 is just 3. That's it. Okay. Now, think about your midline as your new x-axis. So if this is my new x-axis and I'm starting here, then this looks like that. I would really probably think about this one as a sine function. Again, I could start anywhere to count my period, but the easiest way for you to do it is to start at 0 if you can. So if I start here, and then I make one cycle when I get to here, that's when I would start repeating, right? So I'm going from 0 to pi, which means my period is pi. It took pi units to do one cycle. The frequency, super easy. It's just the reciprocal of the period, so that is 1 over pi. Okay. What questions you got? Now, you had another thing you could have done here. This did tell me that 2 periods are shown. So I know if I go to 2 pi for 2 periods, I could divide by 2, but you won't always be given that information. So you need to know how to get it from the graph. Everybody good so far? All right, so let's look at this next one. Go ahead, I'm going to give you a second. I want you to figure out where you think the midline is. So who wants to be brave? Where do we think it is? Y equals 1. Thank you for the y equals. Very good. I do agree with the y equals 1. I think there's a couple of ways that you could think about this. Really, I think that if you just go, all right, I'm here at 3 to -1. That's a total of 4 spaces. The amplitude is going to be half of that, so it's got to be 2 away from there, which that gives you your amplitude, right? You figure out the amplitude while you're figuring out the midline. It's 2. You can also add 3 and -1 and divide by 2. That works out as well, but I think distance-wise is probably a little bit easier for y'all to figure out. All right, so then period. Well, if this is my midline and I'm starting here, then I think it's going to, not that this question even asks me this, but I would think about this along the lines of cosine. So I'm going to start here and end here. So since I'm starting at 0, it makes it really easy. This is my period right here, pi halves. So then what would the frequency be? 2 over pi. It's just the reciprocal. Okay. What questions you got? We good so far? All right, so the next one we're asked for the same things. However, we do not have a picture, and I probably should have moved this example 3 up more so y'all had more room to write down there. Sorry about that. But so this says the sinusoidal function has a maximum point at pi 8. The first minimum after reaching this is at 3 pi -2. Now, the first minimum is an important statement because the way this graph oscillates, you have an infinite amount of maximums and minimums, right? So I need to know it's the next one that comes up so I know what's happening in between. And I'm supposed to find all this. In my opinion, this is impossible to do without a picture, okay? And it's okay if your picture isn't 100% to scale, because just remember that when you are drawing it, it probably isn't to scale. So don't let it confuse yourself. All right. So I have a point at pi 8 at 3 pi. So let's see, I'll make that pi, 2 pi, 3 pi. So pi and 3 pi. And then I have a y value at 8, and I have one like at -2. Okay. A lot of times we don't even care about labeling that stuff, but that's going to be helpful for you here. Don't make 1,000 little hash marks. First of all, you don't have time, and then second of all, it makes it really hard to read. It's okay if they're not really spaced out perfectly. Totally fine. Okay, so I have a point at pi 8, that's here, and that's the maximum. And then my first minimum is at 3 pi -2, like right there. Okay. Now again, I could start anywhere I wanted, but I think I want to start with the first thing that they give me. And if the first thing that they give me is a maximum, then I am looking at a parent function of cosine, right? Does that make sense? So if that is the case, and this is this point right here, that's the maximum, then this is this point right here. You with me on that? Now again, even on here, since I know it's the maximum minimum, I think the best thing to find first before we do anything else is the midline. So look at this, think about it in a minute. See if you can figure out where you think the midline is. Okay, so remember, midline is the middle, right? So if I'm going from 8 to -2, that is a total of 10 spaces, right? Or 10 units. The midline is in the middle of that, which would be 5 units away from the maximum and the minimum. So what would be 5 units away from 8? 3. And 3 is also 5 units away from -2, right? Does that make sense? So be careful getting 5 on the brain and then using 5. When you get there, make sure that these two lengths are the same, whether they look the same on your graph or not. But here's my midline. Okay. Everybody with me so far? So that means my midline is at y equals 3. We've really already figured out the amplitude. What's that? 5, right? Because we kind of had to figure that out. We didn't have to, but we figured it out to help us find our midline. Everybody with me so far? Okay. So then if I come back over here, I have these 2 points plotted over there. Do I have to absolutely plot the rest of it? Maybe not, but this is so new to you, I think it's probably a good idea that you do that. Between these 2 points, halfway is this one right here, which on the parent function is on the axis, but on this would be on my midline. And halfway between pi and 3 pi would be right here at 2 pi, and then I'd have this point, right? So if I keep going, between here and here, that this is at pi and this is at 3 pi. What's this distance then? If I'm at pi and go to 3 pi, this right here is how much? 2 pi, right? So if I'm 2 pi between these two, I got to go another 2 pi, get to 5 pi, to get the other half of it, right? Maximum, minimum, I'd have another maximum right here, and then this would be halfway in between. And whether you drew the rest in or not, you have 5 key points that's all half, half, half. Here is your piece of cosine. Just by those 2 points that they gave me and explained them to me. So now that I have that, I can find the period. I started at pi and ended at 5 pi. What's the distance there? 4 pi. So then what's the frequency? 1 over 4 pi. All right. What questions you got? If you don't draw this out, I mean, maybe so. There's one of you, maybe all day, that could do it in your head, but I doubt it. Like, you need to draw it out and make sense of it, or you're going to get lost in all the stuff. Okay, we good so far? All right, flip it over. Let's look at this clock again. So the prompt here is exactly the same as what we looked at last time. I'm asking you some different questions on it, but this is exactly the same, so we'll go through it kind of quickly since we've already done it. But this figure shows a large clock. It has an 8-inch long moving minute hand. So this is 8. We got to label as we do this. Okay. The center of the clock is 120 inches directly above the floor. So right here, this is 120. Okay. At time t equals 0 minutes, the minute hand is pointed directly up at the 12. So it's right here. At time t equals 0. So at time t equals 0, how far is the tip of that hand off the floor? 128. Then it goes on to tell us that it's not working properly. It's moving twice as fast. So the next time it points directly up is t equals 30. Okay, so also at t equals 30, we're going to be at 128. Okay, because that's one full cycle there. So if it takes me 30 minutes to get back here, how long would it take me to get here pointing at the 6? How long would it take me to get from here to here? 15 minutes. And then what would the distance off the floor be? And it's not 120. 112. Because this is the minute hand, right? I got to subtract that and I get 112 here. Okay. Now, after I get these, I got to make sure I can make sense of what's happening. Is the tip of that minute hand going to be any farther off the floor than 128? No, so that's my maximum. Is it going to be any closer to the floor than 112? No, not unless it fell off the wall, right? So I got two maximums and a minimum. So I can take those and put them on this right here. So this is 0, 128, and then 30, 128, and this is 15, 112. And remember, one beautiful thing about these graphs is everything is half, half, half. So to get this x value here, it's halfway between these two. So 0 plus 15 over 2 is 15 over 2. You don't even have to put the decimal. Probably better if we don't, so we don't divide wrong. And then my y value is also halfway, which I could add these two together and divide by 2. Or in the problem situation, I would be right here, right? And how far is that off the floor? 120. So this is 120. This y value would also be 120. To get this x value, I'm going to do 15 plus 30 over 2, which is 45 over 2. And again, it's safer just to leave it. Everybody with me so far? So we had already gotten all that on the other question and answered some other stuff. But it's asking me now for the period, frequency, amplitude, midline. All right. So period. Again, I could kind of start anywhere. I think I would like to start here. If I start here, then I would end my cycle right there. So the period is the input distance it takes for me to complete one cycle. So what is that? 30. Okay, went from 0 to 30. So then what would the frequency be? 1 over 30. Then the amplitude. What's the amplitude here? This dotted line is my midline, right? It actually tells me that in the question. So what's this distance? 8. It's the minute hand itself. And then the midline is y equals what? 120. It's the y value right there. Okay. What questions you got? We all good so far? All right, so then it says find 2 intervals for when h is both decreasing and concave up. Okay, so here I'm increasing, then I'm decreasing, but that's concave down. Here I'm decreasing, but concave up. Anytime you're asked for an interval, unless you're specifically asked for the range, everything else is inputs or x values. So from here, for this interval here, I'm going to go from 15 over 2 to 15. But I need 2 intervals. That's just one. That's 2 numbers, but that's one interval. The next time this function is decreasing and concave up is right here. And I don't have ordered pairs there, but I should be able to figure them out very easily. I know for this one, at least my y value is 120. Not that that helps me any. And I know that this y value is 112. So notice from maximum to maximum is 1 cycle, but minimum to minimum is 1 cycle also, right? If I start here and I draw this, when I get here, I'd start over again. So from here to here is also 1 cycle. That's just, and the period is what? 30. So if I add 30 to 15, I get 45 here. And then to get this x value, it's halfway between those two. It's easier than dealing with that stuff, right? So 45 plus 30, that is 75 over 2. Like you could find every single other ordered pair you could possibly find if you needed it, but this is going to take me from 75 over 2 to 45. Okay. What questions do you have? All right. So overall, when we get through this stuff, you will find that this stuff is really not that complicated if you were paying attention and staying awake. But if you don't practice this, it's not going to get any better for you. So don't put this off. Practice this now before we get into more stuff tomorrow. All right.